Hello everyone and welcome back. In today's organic chemistry episode, we will be discussing a fundamental organic chemistry topic, alkene reactions. Previous alkene knowledge, we know that alkenes are hydrocarbons that contain carbon-carbon double bonds. With the reactions, when we're getting into these mechanisms, the double bonds act as nucleophiles. Nucleophiles mean nucleus-loving. That's what it means. They are attracted to positive charges or electron-deficient atoms. So a fundamental topic when discussing alkene reactions is Markovnikov's rule. Markovnikov's rule is a guide for determining the regiochemistry. Regiochemistry means orientation of electrophilic addition reactions. In the addition of HX, meaning a hydrogen and a halide, to an alkene, the hydrogen atom bonds to the alkene carbon that has fewer alkyl substituents. We will get into this very soon. These are two depictions of Markovnikov and then non-Markovnikov. In essence, when running a reaction or a mechanism, HX, an alkyl halide, the hydrogen will add to the less substituted carbon. Therefore, usually a methyl or a primary or a secondary if a tertiary carbon is present. So looking at this example, double bond is right here. This is a tertiary carbon. The other carbon that shares the double bond is a secondary carbon. Therefore, the hydrogen will add to the secondary carbon, the halide will add to the tertiary carbon. This is all due to stability. In non-Markovnikov, this is very straightforward. The tertiary carbon, secondary carbon. These are the carbons that share the double bond. The hydrogen will add to the tertiary carbon. Halide adds to the secondary carbon. Now, these are the two depictions, Markovnikov on the top, anti-Markovnikov on the bottom. Now, one thing that is vital to alkene reactions is carbocation stability. We haven't discussed carbocations yet in our channel. Carbocations are simply carbon cations, meaning they've lost an electron. Therefore, they are denoted by a positive symbol. Now, carbocations increase in stability upon substitution. So looking at this carbocation stability, the methyl carbocation is less stable than the primary. The primary is less stable than the secondary. The secondary is less stable than the tertiary. So in looking at these, we've seen these R groups before. R groups simply refer to the rest of a molecule. In this example, we'll just refer to them as extra carbons. So this carbon is bonded to one other carbon. Therefore, it'd be primary, one other carbon. In secondary, there's two R groups. Sticking with our same example, two other carbons. This is denoted as a secondary carbon. And then tertiary, three carbons. This scientific language is general across the entire field of science. We see this in biochemistry, in protein structure, and so on. Now, this is a quite overwhelming chart. This is just an oversimplification of all the reactions you may see with an alkene. When working with alkene reactions, it is pretty much the same sort of trend across most reactions. We're looking at Markovnikov or we're looking at anti-Markovnikov. And then under each cloud, Markovnikov and anti-Markovnikov, we either have carbocations or we don't. So with this chart, we see that alkenes can make all sorts of organic molecules. Alcohols, they can be reduced to alkanes, they can be oxidized, they can make cyclopropanes, epoxides, halides. Halides are some of the more straightforward reactions that we'll deal with, and halohydrons. Halohydrons being a alcohol or a hydroxyl group as well as a halide. So as we move forward with the Markovnikov alkene reactions, I've separated these four main ones into two different groups. These ones are specifically carbocations. The carbon is the cation in the reaction. With these two, we're looking at bromonium ions, chloronium ions for the halogenations. And the oxymercuration-demercuration is exactly what it's saying. We're going to use a mercury ion, specifically a mercury acetate ion, to add an alcohol to an alkene. In this case, the mercury acetate ion will form the cation in the reaction. There will be no carbocation involved, and that same rule applies for halogenation. All right, so now we're going to move into non-Markovnikov, simply denoted as non-Mark. Hydroboration oxidation is the main one we're going to look at. it is very important because it adds the alcohol to the less stable carbon, meaning it's going to be added to a secondary or a primary carbon instead of the secondary or tertiary if there were primaries present. All right, so we've made it to our first mechanism, a hydrohalogenation. Is this Mark or anti-Mark? Okay, so if you guessed right, this is Markovnikov, meaning we want the halide to end up on a more stable carbocation. Therefore, in this case, we have a primary and a secondary. Located in an allylic position, we have two methyl groups. This is not something we have discussed yet, but this can undergo an alkyl shift, meaning we can put the halide on a more favorable carbocation. So let's run this mechanism. All right, so the first thing, nucleophilic attack on the hydrogen atom. Bond breaks, halide gets the electrons, therefore becomes an anion. The hydrogen adds to the primary carbon. The secondary carbon receives the positive charge. When a methyl group is right next door, this can undergo an alkyl shift. So in other words, the methyl group will move. The positive charge is going to go down here. So the halide anion attacks the carbocation, ending up with our 1,3 product. Now that's our hydrohalogenation mechanism. So our second Markovnikov mechanism is an acid-catalyzed hydration. In other words, we're going to be adding a hydronium ion to this alkene, and we're going to end up with an alcohol attached to the more stable carbocation. So our next Markovnikov reaction is an acid-catalyzed hydration. The double bond is going to attack the hydrogen. Hydrogen's going to get sent to the less stable carbon, the less substituted carbon. In this case, this is a secondary carbon, leaving a positive charge on that double bonded carbon. Double bond goes away. In this step, the water is going to attack the carbocation, leaving us with, so the water attacks, it joins to the cyclohexane. Now, look at this. This is very unfavorable. The oxygen in particular does not want to be positive. So a base is going to come through, remove the hydrogen, and leave us with an alcohol attached, this more stable carbon, and therefore we get our product. So as the base removes the hydrogen, the bond breaks, moving the 2 electrons to the oxygen atom, rendering it neutral. Now this is a favorable product. Now there's our product. That's an acid-catalyzed hydration. So let's get into this halogenation reaction. Double bond attacks the bromine diatomic bond splits, rendering the bromine negative. It's an anion now. Now the interesting thing about this mechanism is that this mechanism exhibits anti-stereochemistry. If you picture this molecule like the top of a table, the bromine has added to the top. With anti-stereochemistry, the other bromine atom, the anion, is going to attack from the bottom. This is anti-stereochemistry, also known as anti-addition. Now the opposite of this would be syn stereochemistry, where both atoms add to the same face of the molecule. You can look at this like the top face and the bottom face. This is very important when we run mechanisms to understand which side of the molecule the atoms add to. The bromonium ion is a species that is divalent and positively charged. We know that bromine is a large molecule. It is 35th on the periodic table, so therefore the other bromine must add to the opposite face of the molecule. So the anion is going to attack with anti-stereochemistry, anti-addition. So the bromine anion is going to add to the other carbon that shared the double bond. The bromonium ion will gain electrons and add to the other carbon that shared the double bond. So our end product is a 1,2 halide. So last Markovnikov alkene addition that we're looking at is an oxymercuration-demercuration. It tells you exactly what it's going to run. We're running it with a mercury acetate ion. So let's do this. So the double bond attacks the mercury acetate. A mercurinium ion intermediate will form. The water molecule will add nucleophilically to the carbon that is more stable. Since we're not working with a carbocation intermediate, it's just the carbon that's more substituted. And so therefore, that's where the alcohol will end up. The water adds to the carbon, and just like we saw in the acid-catalyzed hydration, the oxygen molecule has a formal positive charge. So we need to reduce the water. We need to pick up a hydrogen with another molecule of water. Then we reduce the molecule by taking away the mercury acetate with sodium borohydride, and we're left with our alcohol product. This is a hydration through oxymercuration-demercuration. So our last mechanism is anti-Markovnikov, anti-Mark, meaning we're going to be adding a water, this is a hydration, to the less stable carbon, meaning the lower substituted carbon atom. So we're going to run this mechanism. The double bond is going to attack the hydrogen attached to the boron. The electrons from that bond go to the boron atom. Because the boron atom has only 6 electrons in its valence shell, it makes it extremely reactive. So when a THF solution, BH3, accepts an electron pair from the solvent molecule in a Lewis acid-base reaction, this completes its octet to form a stable BH3-THF complex. The reason this reaction is so important is because hydroboration is useful because of its regiochemistry. This adds syn stereochemistry, meaning in the process, boron and hydrogen add to the alkene from the same face of the double bond. This is the opposite of anti-stereochemistry. So this is our organoborane intermediate. Upon addition of hydrogen peroxide and a base, we will receive our final product, the alcohol. This alcohol, via anti-Markovnikov rules, is on the less substituted carbon. This is secondary, this is primary. So I hope you found this video insightful. I'm going to leave some timestamps in the comment section, so if you're looking for a particular mechanism, you can go find that mechanism and get away with your practice problems. Thank you so much for watching. We'll see you guys in the next one.